Alright, AP Stats. So I found out last minute that I was not going to be there for you today, so I'm going to go ahead and go through this section of notes with you. We are still going to get through chi-square tests for independence as well as using tests wisely. So let's first talk about what chi-square test for independence is and how it's slightly different. So chi-square test for independence, when you are talking about that, basically the idea of association between two variables is what makes a chi-square test for independence different. Really all it ends up being is a slight difference in wording. And so really with that being said, what you're really going to be testing is this idea of association versus no association. So that's going to be kind of the first thing that's different, is going to be that idea of association versus no association instead of comparing two distributions, which is what we've been doing with chi-squared for homogeneity. The next thing we're going to talk about here, with two variables being independent. Basically what this is used to determine is it's used to determine if one variable depends on or is influenced by another variable. In other words, what we're going to be able to do now is not only talk about if two distributions are different, we're going to be able to talk about association versus no association and start to establish a cause and effect relationship. Now, we're never actually going to be able to establish cause and effect, but association is about as close as you can get to doing that. So to answer this question, how is a test of independence different than a test of homogeneity? Basically, what we're looking to do here is that we compare association instead of comparing two distributions. So now we're not so much worried about is one distribution closely following another distribution. In other words, we're not as concerned with does it match what was expected so much as is there a way, can we show that one of these variables is in a way associated with the other variable? In other words, is one influenced or does it depend on the other? So how do you state your hypotheses for a test of independence? The good news is you do it the exact same way. Really the only difference is you use association instead of talking about the distribution. So you can see how this is going to be very similar. And this is, again, how you're going to be able to distinguish independence from homogeneity is in your definitions and in your hypotheses, specifically when you're working through a problem. The good news here, too, is that all the calculations are the same as well. So you're still going to be using that chi-square test button. It's still going to autofill the values into your second matrix for your expected counts. So the good news there is that that is all the same. So yeah, really, I'm not going to give you a whole lot of formulas for these. Expected counts, that is the same as for homogeneity. If you do need that kind of written out for you, that is where you take row total multiplied by column total, and then divide by the overall total. So if that was something that you were needing to write down, there it is. The test statistic is still going to be chi-squared. I'm not going to give that one to you. That one's in your notes for homogeneity. It's also on your formula card. And I think we talked about that when you took your quiz on Tuesday. So yeah, just keep in mind it's the exact same. Degrees of freedom, exact same. If you need to write that down again, that is number of rows minus 1 multiplied by number of columns minus 1. Okay. So then when we get to our conditions, again, these are the exact same, so I'm not going to waste our time with writing all those out for you. But the conditions for a test of independence are the exact same. Keep in mind that this is where all expecteds must be greater than 5, not greater than or equal to. Greater than or equal to only works for goodness of fit. All right, so enough with that stuff. Let's get to an example. This is one of my favorite examples. Is your index finger longer than your ring finger? And does this depend on your gender? Random sample of 460 high school students in the U.S. was selected and asked to record if their pointer finger was longer, shorter than, or the same length as their ring finger. Mine are pretty much the exact same. The gender of each student was also reported. So here's your data that was summarized in this table below. So you can see that they surveyed roughly equivalent numbers of male versus female, and that it was fairly split. I wouldn't say 50-50, but fairly well split between the three different lengths of fingers. Um, so in part A, make a graph to investigate this relationship between gender and relative finger length. Describe what you see. For this, we're just going to make a bar graph, and remember, your graphing needs to be a little bit different for categorical. You can't really use histograms or box plots or a lot of those other types that you normally would. So we are going to actually make a um, bar graph, and I'm going to make it a side-by-side bar graph. If you want to do the same, feel free to do so. I'm going to put frequency as my label over here on the left side, and I'm going to make your length over on the x-axis. So we'll do index longer as the first category. We'll do same as the second, and then we'll do ring finger as the final category there. So frequency, if you notice, all of the totals for each of these, and we're going to compare male versus female. So when I say side by side, we'll make female blue, we'll make male red. So we'll compare those side by side. And if you notice, they go up to 116. So to make it a more round number, I'm going to say 120. So halfway would be 60. Halfway between these would be 90. Halfway here would be 30. Here would be a tick mark for 15, 45, 75, and then 105. Okay, so let's make this here for female is in blue. 85 is what the one category was for index. So we'll take that up to about 90 there, bring it back down, and if you want to shade it in, you can. For same, 42 for females, so that would be a little bit below that tick mark we made for 45. So about something like this. And then for ring finger, we had 100 for females. So that would be all the way up to about that 105 mark. And there's females. All right, let's compare how males would have been. So for males, 73. Let's see, that would have been a little bit below 75, so that would have been about right here. For it being the same length, 44 is pretty much right at that line of 45, a little bit above. So about right there. And then for ring finger longer, then those 116 would be almost to that 120 mark, which was the highest mark, which would be right about in here. So the first thing, describe what you see. At least to me, it does not appear like there is an association between gender, or I guess sex would be the more appropriate term there, but between gender and finger length. Because really, if you notice, they're all pretty close to each other. It's not as if all of females have significantly larger index fingers than males. I mean, a little bit, but not much. The same length is almost the exact same, and ring fingers, again, is pretty close. So to me, it does not look like there's an association. It would, if there was going to be an association, what I would expect is that females would maybe be skewed one direction and males would be skewed the other direction, or something along those lines. But to me, it really doesn't look like there's an association between the two. But that's just looking at a graph. So let's get some statistics that can maybe help us with making a more formal decision there. So does this data provide convincing evidence at the 5% significance level of an association between gender and relative finger length for high school students in the U.S.? All right, so here's where we're going to go through that 4-step process. So starting with step 1, let's talk about our null hypothesis. We're going to start with the assumption that there is no association. Oops. So there is no association between gender and finger length. And then for your alternative, you would say that there is an association, and then at that point, I'll let you kind of fill in the rest of dot, dot, dot. But essentially that's the same as your null hypothesis, just kind of filling the rest of it out. All right, so significance level. This time it actually told us significance level, but it still wants us to use 5%. So let's get into our conditions and checking. So we are going to be doing a chi-square test. Notice that you don't need to specify independence because that's what your null and alternative hypotheses did. So the first condition, we have to ask ourselves, was this a random sample or random experiment? And if you look up here, it does say a random sample of 460 high school students, so we met the randomness criteria. Next thing, 10% condition. There were 460 people in the sample, multiplied by 10. Is it reasonable to assume that there would be more than 4,600 U.S. High school students that we could pull from? And most definitely. Last thing here are all of our expected counts greater than or equal to 5. That's going to be one that we're going to have to kind of wait to see until we actually do our significance test. So remember to go back and we'll have to double check for that one. All right, so let's get all this typed into our matrix. I'm going to zoom in on this data so you can see a little bit more clearly, and then we'll put this into matrix A. So on your graphing calculator, let's go to the matrix menu. Maybe we'll go to the matrix menu if it'll work for us here. We'll try restarting it. How about that? Just like in class, right? Okay. So at this point, it looks like we're up and running. So let's go into that matrix menu. Let's get all those typed into matrix A. Keep in mind that this time, if you want it to look the exact same, you're going to have to do a 3x2 matrix, 3 rows by 2 columns. So for the first row, 85 and 73 there. For the second row, 42 and 44. And for the third row, 100 and 116. Okay, so now let's do our significance tests. We're going to go back into stat, over to tests, go up to our chi-squared test. And in chi-squared test, our observed we put in matrix A, expected will be put into matrix B. We do our calculations, and voila, there we go. So at this point, let's go ahead and write down our information for our do step, which is this step 3 that we are currently working on. Oops. Apparently my pen's going to freak out on me. Okay, we'll try this again. All right, this was the 4,600. All right, now we're back in business. So let's see, chi-squared was equal to 2.06. Let's see, we had a p-value of 0.356, and we had a degrees of freedom equal to 2. All right, let's go back in and let's check to make sure all of our expected counts are greater than 5. So back to matrix, over to edit, we'll look at matrix B, and they all look good. All right, so our last condition was met. We are good to go there. Okay, so last thing that we need to do is we need to write our conclusion. So because our p-value, man, it's giving me a hard time here, but because our p-value is greater than our significance level of 0.05, we would fail to reject our null hypothesis. In other words, there is not convincing evidence of an association. So notice that we have again here changed from distribution to an association between gender and relative finger length. Okay, cool. So let's see. Last part that we need to address here, if your conclusion in part B was an error, which type of error did you commit, and explain. So let's see. Based on our conclusion, which was that we failed to reject our null hypothesis, The only type error we can make is a type 2 error. And then explaining that is that, we could explain that because we did not reject the null hypothesis would be kind of the initial reason why it's a type 2. But as far as what a type 2 error would be, that would be to say that we did not find evidence of an association between gender length or gender and relative finger length when there really was an association. Okay. Guys, that wraps up our notes for chi-square tests for independence. As you can see, really the only difference is in the wording of the null and alternative hypothesis, as well as what you look at in the conclusion. Everything else is exactly the same as what you would have done before. So that'll wrap up our notes for this part of the notes. I'm going to record the video for using chi-square test wisely, just so that it's not too big of a file. So check on Schoology for that as well. And then when I get back on Monday, since we don't have school on Friday, we'll go over kind of how to know what type of chi-square test to use based on the information you're given, and that'll also be our review day. All right, so I will see you guys then. Have a good rest of your day today, whether it's Wednesday or Thursday, and I will see you on Monday. Have a good weekend.